Okay, hello everybody, we start, and today's section 14.1, absolute and conditional convergence of improper integrals. So I'll start with definition. Improper integral a to b f of x dx is called absolutely convergent if integral of modulus converges. So here both types of integrals are included together, and in fact even more. I mean, doesn't matter how many singularities where our function is unbounded, and if maybe a is minus infinity, maybe b is plus infinity, maybe both, so minus infinity less or equal a plus b less or equal plus infinity here. So it doesn't matter how many singularities we have, and if function is unbounded in some neighborhoods, so doesn't matter. So once again, absolutely convergent means that integral of modulus is convergent. And now simple proposition 1. If integral is absolutely convergent, then it converges. So in principle, I mean, without any additional information, it could be that absolutely convergent integral is divergent in itself, right? According to the definition. So we put into the definition that we ask the convergence only for that integral, and we say nothing about the integral itself, right? So in principle you can say, oh, it might be this is convergent, but that is not. But it cannot happen. So if it is absolutely convergent, then it is convergent itself. And proof, we use Cauchy criterion. So once again, let me draw the chain of implications. So we start with what we suppose. Integral is absolutely convergent. Absolutely convergent. Then by definition, integral of modulus converges. Okay, then we use Cauchy criterion. And without loss of generality, I'll suppose that we have singularity only near B, doesn't matter which, finite or infinite, because we formulated Cauchy criterion for this case, so I'll use just that one. So by Cauchy criterion, what we can say? For arbitrary positive epsilon, there exists, okay, let it be delta greater than A, such that for all delta less B1 less B2 less B, for all, okay, maybe for all B1 B2 such that delta less B1 less B2 less than B, we have an equality modulo integral from B1 up to B2 modulo f of x dx less than epsilon. Okay, then look, here we have modulus inside. It means this is non-negative integral, so we may forget about the integral, and let me estimate now so what I can deduce directly. So I'll rewrite again the same sequence of quantifiers for arbitrary B1 B2 such that delta less B1 less B2 less than B. We have now chain of inequalities. Integral from B1 up to B2 f of x dx. Modulus of integral is less or equal than integral of modulus. Estimate for integrals. So we suppose the function is integrable on arbitrary interval, which is from a to some number smaller than little b. And now you see, this is non-negative, and according to our Cauchy criterion, this is less than epsilon. Then, again by Cauchy criterion, we deduce, if modulus of integral less than epsilon, we deduce the integral from a to b f of x dx without modulus converges. So you see, usage of Cauchy criterion allows us to deduce it almost immediately. Just simple estimation of the integral works very quickly. And you see, now how we can proceed with proofs of absolute convergence of integrals. So, for example, comparison test. It works as a test for absolute convergence as well. So let me give, because look, if we have modulo f of x less or equal than modulo g of x, and integral g of x dx converges absolutely, then integral from a to b f of x dx converges absolutely. Of course, you should suppose functions are integrable, Riemann integrable, and so on. I didn't formulate it rigorously, just to show how it works. Because why? Look, what means converges absolutely? Means integral of modulus converges. Comparison test says if two non-negative functions satisfy this inequality, then from convergence of great integral follows convergence of smaller. So integral of modulus of f converges, and it means the integral f of x dx converges absolutely. That is how simple chain of conclusions works. Okay, let me consider a couple of examples. So, example 1, we consider the integral square root of x over square root of 1 plus x power 4 dx. Look, that is a good example to show how equivalence works. Because, look, what we know, square root of x over square root of 1 plus x power 4 is equivalent to what? As x tends to plus infinity. If x tends to plus infinity, then we may forget about 1, and what we have? X squared in denominator, so square root of x, it means 1 over x 3 over 4, 3 over 2, sorry. 3 over 2, as x tends to infinity, right? So, if we multiply, then we obtain limit equals to 1. And what it says? Let me recall what it says. Equivalence. Equivalence by definition says limit as x tends to infinity, square root of x over square root of 1 plus x power 4 divided by 1 over x 3 over 2 is equal to 1. Hence, for example, what we can deduce? We can deduce there are constants and there exists delta greater than 0 such that for all x greater than this delta we have inequality square root of x over square root of 1 plus x power 4 over 1 over x 3 over 2 is, let's say, 1 plus 1 half and 1 minus 1 half. So, this follows from properties of limits of function. So, limit equals to 1, so it means values of our function are close to 1 for sufficiently large x, because x tends to infinity. Now, what it means, let me rewrite it. 1 half times 1 over x 3 over 2 less or equal square root over x over square root of 1 plus x power 4 less or equal 3 over 2 times 1 over x power 3 over 2. That is valid for sufficiently large x, right? But if we are interested in convergence of an improper integral, then it doesn't matter where we start. Why? Because for integral from 1 to delta, we have no question. The function is continuous under integral, right? Hence, the integral is a number, finite number, and we can forget about it. So the question is, in the improper integral for the rest, for this one. And here what happens? Here we have such inequality. So in particular, I may use just the right half of this inequality. What we know? We know the integral from 1 to plus infinity dx over x power 3 over 2 converges since 3 over 2 is greater than 1. Let me recall. We started integrals dx over x power alpha. From 1 to infinity, it converges when exponent is greater than 1. 3 over 2 is greater than 1. Hence, this integral converges. Hence, integral from delta to infinity converges as well. And then, okay, multiplying by a constant changes nothing for convergence, right? And it means large integral converges, hence small integral converges as well. So it follows from comparison converges. Comparison. And since all functions are non-negative, then, and of course we should suppose it, that it's greater or equal to 0, otherwise comparison test doesn't work. Hence we deduce that our integral is absolutely convergent. Absolutely converges. And that is always the case. I mean, for non-negative functions, it makes no sense even to say about, convergence is the same as absolute convergence for non-negative functions, right? Because absolute convergence means convergence of absolute value of. Okay, one more example then. Also typical. Okay, example 2. One to infinity cosine x over x squared dx. Here we can write the following estimate. Cosine x over x squared is less or equal than 1 over x squared for all x greater or equal than 1. Then, since integral from 1 to infinity dx over x squared converges, once again, 2 is greater than 1, like here, right? If exponent is greater than 1, the integral from 1 to infinity converges. Put in polynomial in the numerator. Why did you put that in? Why did you put that in polynomial in the numerator, the limit in previous example? I guess this is about that one. That is, what means equivalence? Equivalence means this limit of ratio is 1. We discussed some time ago symbols capital O, little o, and equivalence, right? Equivalence means ratio tends to 1. Once again, this follows from an example which we considered before. Converges, it was an example, if and only if alpha greater than 1. This was former example, right? Now, from 1 to delta we have no problem. What happens between 1 and delta? Same as for this integral. Continuous function, so integral gives finite number, right? Same situation here. From 1 to delta, integral from 1 to delta dx over x power alpha is a finite number. So, doesn't matter. Either we consider integral from 1 to plus infinity or integral from a positive delta to plus infinity. That's absolutely equivalent things. Why? Because integral from 1 to delta is a constant. So that is why we don't care about it. Okay. So, but here even we don't need to change lower limit, doesn't matter. So we go from 1 to infinity, right? It converges. Then comparison test. So comparison test says integral from 1 to infinity modulo cosine x over x squared dx converges, and by definition it means that integral from 1 to plus infinity, okay, infinity doesn't matter, cosine x over x squared dx is absolutely convergent. Okay. Now let's go to the next definition. So we considered absolute convergence. Now conditional convergence. Definition. If the integral from a to b f of x dx converges but not absolutely, then we say it converges conditionally. Concerning meaning of words absolute and conditional convergence. With absolute convergence it's clear, right? We put absolute value, so quite logical to call it absolute convergence if it converges when we put modulus or absolute value, in other words. But For the word conditionally, this is not clear now, unfortunately. And for conditional integrals, I cannot explain why it is used. This is, in fact, in analogy with series. A little bit later we'll consider series, and for series the word conditionally will be explained. Okay? So wait a little bit for an explanation for this word. Okay. And how conditional convergence can be proved? We need a tool to prove convergence of integral if we don't care about modulus. I mean, it means we cannot use comparison test. Then what we'll use is called Hubble-Dirichlet test. So Theorem 1, Hubble-Dirichlet test for improper integrals. Later more tests with the same name will appear, so that is why I include here words for improper integrals. So okay, I think I'll consider it for a particular case. So suppose, I mean, particular in the sense that we have a singularity near B. Suppose f, g are Riemann integrable in fact, I can suppose only for f, it doesn't matter. On any a, b tilde, so for arbitrary b tilde, a less b tilde less b, which can be infinity as well, maybe plus infinity. Okay, moreover, no, let it be like that. Then, sufficient conditions for convergence of the integral f of x g of x dx are the following. The first one, let me start with Latin. First one, Dirichlet. test also is called. It has two. First, integral from a, okay, let it be capital F of x equal to integral from a to x f of t dt is bounded on a, b. And second, g of x is monotone on AB and limit as x tends to b maybe minus g of x equals to 0. That is couple of conditions for Dirichlet test. And another pair consists also of two conditions, and it is called Abel's test. Abel test. The first one is the following. Integral from a to b f of x dx converges. Second, g of x is monotone on AB and bounded on AB. So once again, how to understand that couple of sufficient conditions? So either this pair of suppositions is supposed to be satisfied, or another pair of suppositions, and both of those pairs imply the convergence of this property. And proof is quite analogous for both. So for the proof, what we'll consider, we'll proceed by Cauchy criterion. So Cauchy criterion says integral from a to b f of x g of x dx converges if and only if for arbitrary epsilon greater than 0 there exists delta greater than a such that for all b1, b2 satisfying inequalities and b, we have the estimate integral from b1 to b2 f of x g of x dx less than epsilon. So what we need to prove is that line of the Cauchy criterion. And how we proceed with it? Look, we apply second mean value theorem or Bonnet formula. Second mean value theorem for integrals. Bonnet formula formula. So why we can apply it? Because in both pairs there is a supposition about g of x should be monotone, right? And if g of x is monotone, we can take it outside. So this is equal to g of b1 times integral from b1 to psi f of x dx plus g of b2 times integral from psi to b2 f of x dx. That is Bonnet formula. So there exists psi in b1, b2. b1, b2. That is according to Bonnet formula. So second mean value theorem allows to put, roughly speaking, monotone function outside of the integral. So like a constant in such a manner. That is how second mean value theorem works. Now, how we'll proceed? So we have pair of suppositions. So I'll proceed, of course they're analogous, but let us proceed separately. So first, Dirichlet. Capital F is bounded. Let me write it. There exists a constant C such that for all x from A to B, we have capital F of x less or equal than C. And then limit as x tends to B maybe minus if B is finite, if B is infinite. We don't need to put minus here. G of x is 0 implies, again by definition of the limit. So for arbitrary epsilon greater than 0, there exists delta. Delta is not good. Okay, let it be delta 1 greater than 0 such that for all, okay, maybe I'll use same delta, doesn't matter. Then for all x which are between delta and B, we have an equality g of x is less than, let's say, epsilon over 2c. The question about the first test, you mean first half of the Hubble test, doesn't that mean that it is absolutely convergent? No. We only suppose integral from A to B converges, nothing else. No, we don't need to suppose that it converges absolutely, no. Only convergent, nothing else. We don't suppose that it is absolutely convergent. Okay, let's have a break. Okay, let's continue. So, once again, I modified a little bit the meaning of delta, right? So, usually, what is delta, which is positive? Here it should be greater than a, by the way, right? Not 0, greater than a. Usually delta indicates neighborhood of b, right? But now I don't exclude the case when b is infinite. So b might be finite and maybe infinite. So to avoid different notations, I use one notation which unifies both neighborhoods. I mean neighborhood of infinity and neighborhood of b. So what means neighborhood of finite b or infinite b? So x should be sufficiently close to b from the left hand side. Sufficiently close to plus infinity means x is greater than some number, right? Sufficiently close to b means, okay, again, same inequality. So in usual definition we have b minus delta, but doesn't matter. I can denote b minus delta by delta, no problem. Okay, that is just the definition of the limit of a function. Now look, compare it with our Bonnet representation. Look what we have. So if I choose same delta as here, right? Look, here there exists delta, right? So I want to prove Cauchy criterion, right? It means I want to prove this line. It means I take arbitrary epsilon greater than 0, right? Then look at the definition of the limit. There exists delta greater than a. Okay? Same delta I choose here, right? Then what happens for arbitrary capital B1, B2? So I take arbitrary B1, B2 which satisfy this inequality. I apply Bonnet formula like that. There exists psi somewhere between, right? And then what I do? G of B1 is strictly less than epsilon over 2c. Why? Because what we supposed? We supposed B1 greater than delta. So it works, right? Instead of x, we take B1. G of B1 less than epsilon over 2c. Also, G of B2 is less than epsilon over 2c as well, right? And then, so, what I used? I used this. G tends to 0. Right? I have used it. Okay, good. Now, we have one more condition. Capital F is bounded. Capital F is less or equal than c. And then, look. Oops. I was mistaken a little bit. Let me change a little bit. 4c. 4c. Sorry. It's better. Bonnet. 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 Okay. So, what is integral, let's say, from B1 up to psi, f of t dt? We can represent it as integral from a to psi, f of t dt, minus integral from a to b1, f of t dt, by addition No. Just for C here, yeah. No. That is a bad idea to change to C to G will be 1. No. G will be 1 less than epsilon over 4C. Sorry. 4C here also. 4C. So, go back. Integral from B1 to Xi, f of t, integral from A to Xi minus integral from A to B1. That is additivity property, right? Additivity property of the integral, right? Additivity property of the integral. And that is what? That is capital F of Xi minus capital F of B1. So how I can estimate it? I put modulus less or equal modulo F of Xi plus modulo F of B1 less or equal to C, because values of capital F are bounded by capital C. So then what it means altogether, look, go back to our Bonnet formula. This term less epsilon over 4C, this in modulus less than 2C, and same is here, less epsilon over 4C less 2C in modulus. Altogether, what we have? Epsilon over 4C times 2C, epsilon over 2 plus epsilon over 2. Epsilon, right? So, we proved. The estimate modulus of this less than epsilon. That's it, right? So, for Dirichlet test, we are done. Now, go back to the second half. So, Hubble test. The last part. The last part. Which last part? Here additivity is used, right? Then, okay, modulus of this less than 2C is directly that one, right? Is it clear? This is estimated by 2C by that one, right? Precisely. In modulus. For this one, the same, right? The same consideration works. Less than 2C. So, that is how it works. Yeah. Okay. Okay, now for the second part. Now I'll use convergence of integral of f of x dx. Converges. Hence, we can use Cauchy criterion for the convergence for that integral. So, for arbitrary epsilon greater than 0, there exists delta greater than A, such that for all B1, B2 which satisfy the inequality delta less b1 less b2 less than b, we have the estimate integral from b1 to b2 f of x dx is less than, and instead of epsilon now I'll use epsilon over 2c, where not c, let it be different, to m, where m, what is m? Where m is such that g of x less or equal to m for all x greater than a. Okay, from a to b. We suppose, look, in second supposition, we suppose g of x is bounded. Okay? G of x is bounded, that is g of x less or equal to capital M. Right? Bounded. Okay? And just that M is used here. Now, go back to our Bonnet formula. Go back to our Bonnet formula. Look here. So now look, psi is somewhere between b1 and b2, right? And it means that, again, I use Cauchy criterion. So take arbitrary epsilon greater than 0. I choose delta from Cauchy criterion for that integral now, right? I used Cauchy criterion and I found delta. Then, what I can do for arbitrary b1 and b2 which satisfy that inequality? What we can do? Look. I look at this integral. b1 and psi both satisfy that restriction, right? Because psi is between b1 and b2, right? So it means I can estimate integral from b1 to psi by epsilon over 2m, right? So this integral is less than epsilon over 2m by modulus, of course, right? By this Cauchy criterion. And g of b1 less or equal to m in modulus, because g of x is bounded, right? Same estimation works here, right? So less or equal m, roughly speaking, in modulus, of course, when we estimate. So m times epsilon over 2m, we estimate the first term by epsilon over 2, and same estimate for the second term, right? So altogether, we proved this equality. So we proved our result, and let me look once again how we proved it and how it works. Look, so we used second mean value theorem, right? And we have two terms, both are estimated in analogous way. And look how they are estimated. One of them is bounded, another is very small. For Dirichlet test, that is bounded, that is small, because g tends to 0, right? And integrals are bounded. And for Hubble test, that is bounded, and this is small. So we have product, and roughly speaking, you put more restrictions to one term of the product, right? And then you can ask less restrictive things about other term. So look for Dirichlet Hubble test. In Dirichlet, little f has bounded primitive, right? G is infinitely small. For Hubble, you should suppose little f has convergent integral, improper integral, but g of x may be only bounded. So that is how it works. Okay. Integral of f of x dx from psi I to b2 is less than epsilon over 2m again. Epsilon over 2m. Same estimation. For the second, from psi to b2, again we apply the same estimation, right? Because that is once again both psi and b2 satisfy that restriction. So we can work here in the same way as for the first term. Okay. Now, how everything together works. And let me consider classical example, that is model example, I would say. How to proceed with investigation of convergence. So, okay. I think that we won't get f of x, g of x dx less epsilon because it would not get simplified. Why? Again, Bonnet formula. What is different for psi to b2? What should be simplified, I wonder? We don't simplify anything. We have a product and we estimate. Firstly, we represent it in Bonnet formula. Yeah. Okay. Okay. So. Now, example. In this section, this is third example. And investigate integral, okay, let it be sine x over x power alpha absolute and conditional convergence. And conditional convergence. Dependent on alpha, of course, right? So, solution. That is typical solution. That is, I would say, 3 branches. We have 3 branches, and that is very, very typical in examples where you need to study to investigate absolute and conditional convergence of an integral, and especially if you have a parameter inside. Alpha is arbitrary parameter, so you should clarify when your integral converges absolutely, when it converges conditionally, and when it diverges also. So, first, let us start with very simple estimation. You see, this estimation works always, right? I mean, it is valid. Sin x is less or equal than 1. Good. And then we know the integral converges if and only if alpha is greater than 1. That is also what we know from an example from former lecture. Now, look, what it gives to us. Our integral, what can we say about our integral? Is absolutely convergent for alpha greater than 1. Because of comparison test. So, we estimate our function in modulus by another function, and we know that that integral converges if alpha is greater than 1. But let me emphasize. You see, here we have in both directions, right? But you cannot assert now that it is absolutely convergent if and only if alpha greater than 1 at that moment. Why? Because you use comparison test, right? And it says, if large integral converges, roughly speaking, then smaller converges as well, right? But it doesn't say if this is divergent, then that is divergent as well. No, definitely it is not true. If larger integral diverges, smaller may be convergent as well, right? You cannot deduce. So, if alpha is less or equal than 1, this integral diverges. Hence, this inequality says nothing for us. So, for alpha less or equal to 1, no conclusion at all at that moment, right? So, this simple estimate gives only this assertion, nothing else. So, at that moment, we deduced absolutely convergence for alpha greater than 1. Even we don't know if it is not absolutely convergent for alpha less or equal to 1. No, we cannot deduce. Okay. Now, nevertheless, okay, second step, apply Dirichlet test. So, we have a product of two functions, f of x is sine x, g of x is 1 over x power alpha. What can we say about primitive? Capital F of x, which is integral from 1 to x sine t dt, that is minus cosine t from 1 to x minus cosine x plus cosine 1. And you see, obviously it is bounded. Modulo f of x less or equal than 2, right? For sure. So, first condition of Dirichlet test, boundedness of a primitive is fulfilled. Second condition. Second condition says for Dirichlet test, g of x is monotone. True? True. For arbitrary alpha, this is true, right? 1 over x power alpha is monotone. Either increasing or decreasing, doesn't matter. And also g of x tends to 0 as x tends to infinity. When it's satisfied? For alpha, which alpha? When 1 over x power alpha tends to 0 as x tends to infinity. The exponent is positive, right? Roughly speaking, if x is in denominator, then it tends to 0 as x tends to infinity, right? Otherwise, it doesn't tend to 0. So for alpha greater than 0, right? So it means that Dirichlet test works for alpha greater than 0. So what we conclude? Hence, Dirichlet test, what it says? Our integral converges for alpha greater than 0. Nothing else. You may ask me, why we did it? For example, for alpha greater than 1, we know more, right? We know our integral converges absolutely for alpha greater than 1. Why we considered that Dirichlet test for alpha greater than 1? You are right. For alpha greater than 1, we have no new information at all. Right? It doesn't give any information. For alpha from 0 to 1, what it gives to us? Again, nothing definite. We know the integral, our integral, converges. But we don't know at that moment how it converges, absolutely or conditionally. Why? Because we don't know if the integral of modulus converges or not. We don't know at that moment. So, then, what we do? Third, in fact, we can expect that, look, it works very often, in fact. If you have absolutely convergence for alpha greater than 1, and you have convergence for alpha from 0 to 1, you may expect that it is conditionally convergent, right? But what you need to prove for that reason? If you want to prove that your integral is conditionally convergent, you should prove that it converges itself, but for modulus you have divergent integral, right? It means that prove that integral converges conditionally for alpha from 0 to 1. So what we know for those alpha? We know it converges, right? But we don't know how. So it means to prove that it converges conditionally, we need to prove that's equivalent to say that this integral of modulus diverges for alpha from 0 to 1, right? At that moment, be careful, I wrote here equivalent. Why it is equivalent? That is equivalent because of what we did before, right? So in second step, we have proved that our integral converges for those alphas, right? And once we know it is convergent, then conditional convergence is equivalent to divergence of the integral of modulus, right? If we know that the integral itself converges, then conditional convergence is equivalent to divergence of the integral of modulus. And now look, to prove divergence of non-negative function, we again use comparison test. But to prove divergence, it should be in opposite direction, right? Comparison test works when we want to prove divergence of something, means that we need to find something which gives an integral smaller but nevertheless divergent. And it turns out that is sine squared x over x power alpha. Why? Because modulus sine is a number which is between 0 and 1, right? And if you take a number from 0 to 1 and take square, it will be smaller, right? So it means that modulus sine x greater or equal than sine squared. That is typical thing which works in many examples of this kind. Now look, we know what is sine squared. We can represent it using trigonometric formulas. 1 minus cosine 2x over 2x power alpha, right? And now look, integral from 1 to infinity, 1 minus cosine 2x over 2x power alpha dx equals to integral from 1 to infinity, dx over x power alpha 1/2 minus 1/2 integral from 1 to infinity cosine 2x over x power alpha dx. Now look, converges by Dirichlet test. For alpha greater than 0. Similar to 2. Similar to 2. Look, what is different? Instead of sine, I use cosine 2t. So once again, the primitive is bounded. That, as we know, for alpha between 0 and 1 diverges. So diverges for alpha from 0 to 1. And once we have a sum of two objects, one of them has a limit, converges, right? Another doesn't have a limit, diverges. It means their difference is divergent, right? So, hence, this diverges. Right? And look, smaller integral diverges, hence larger diverges as well. So we are done, right? So it means we checked conditional convergence for alpha from 0 to 1. The last step. Usually second and third are unified into one. So we have, as I told, 3 branches. Second and third step is one branch. You see, in both cases, Dirichlet test works, right? Now, for fourth step, integral from 1 to infinity sine x over x power alpha dx diverges for alpha less or equal to 0. Here we work with Cauchy criterion. Cauchy criterion. So, there exists L epsilon greater than 0, I mean negation of Cauchy criterion, such that for arbitrary delta greater than 1, there exists B1, B2, delta less B1 less than B2, such that integral from B1 up to B2 sine x over x power alpha dx should be greater or equal than epsilon. So negation of Cauchy. Negation of Cauchy. So how it works? Hubble and Dirichlet says only about convergence, nothing about absolute or conditional convergence, nothing. Okay, how it works? Look, for example, inequality sine x greater or equal than 1/2, when it is satisfied, it's equivalent to pi over 6 plus 2 pi k less or equal x less or equal 5 pi over 6 plus 2 pi k. K is integer, right? That is trigonometric inequalities. Sine equals to 1/2 for pi over 6 and 5 pi over 6, and it means that is. So, that is what I took. B1 pi over 6 plus 2 pi n. B2 is 5 pi over 6 plus 2 pi n, where n is natural now. And you see, since n is natural, it means for arbitrary delta, I can find B1 and B2 which are greater than this delta, because we have here natural, right? Arbitrary natural, so it might be larger. And then what happens? X from B1 to B2, then sine x over x power alpha greater or equal 1/2 1 over x power alpha greater or equal. Now look at alpha. Alpha non-positive, right? So roughly speaking, x is a numerator. So smallest value is at B1, 1/2 B1 power alpha, minus alpha, sorry, minus alpha. Minus alpha is non-negative now. So it is non-negative. Okay, I can write greater or equal than. Okay, So let me write it. What is it? 1/2 pi over 6 plus 2 pi n power minus alpha. N tends to infinity, right? Exponent is non-negative. So if it is 0, then it is 1, otherwise it tends to infinity, right? So what we can deduce? It will be greater or equal than 1/2 for sufficiently large n. N greater than n naught. And it means, look, it means that integral from b1 to b2 sine x over x power alpha dx is equal to integral from b1 to b2 sine x over x power alpha dx greater or equal than 1/2 times the length is 4 pi over 6, 2 pi over 3. So, and that is our epsilon, which is positive, right? So by Cauchy criterion, we proved that our integral diverges for alpha less or equal to 0. So investigation is completed. For non-positive alpha diverges, alpha from 0 to 1 converges conditionally, greater than 1 converges absolutely. That's all. Okay.